conjectures are resolved. And so the way to do it was to note, well, there is a sub-Hopf algebra here generated by polylogarithms. I would put letter L, so motivic polylogarithms, and the same thing here, I guess, but maybe it was a letter C. And if you just look at that sub-Hopf algebra, the formulas for coproducts, for multiplication, they're all completely combinatorial, so you can just define a certain combinatorially defined Hopf algebra and Lico algebra, H dot F. And the Lico algebra I'll use L for, because that's the notation we use everywhere at the moment. So this is just a Hopf algebra generated by formal symbols which are Lie with some indices with some variables. And they satisfy the minimal, so they satisfy the combinatorial formulas for the coproduct the same way as in the motivic world. And they satisfy the minimal set of relations that you have to put on everything for it to be consistent. You don't require any other relations at all. And so basically what you do is, so you define, so delta and the bracket are combinatorial formulas, combinatorial formulas on Lie, or on maybe on the iterated integrals. And then you have to say what the relations are. And what you do is, in weight 1, you just kind of impose this isomorphism by force. And everything else after that you define inductively. So relations in weight n. And I will only do it for the Lico algebra because it's easier. So you say if you have f an element of Ln of f of t, you kind of do it inductively, but you have to define relations in weight n for all fields first, and then you do it for the next weight. If you have an element which is killed by the co-bracket, then kind of it should be a constant function in some sense. So this should be a relation in the smaller field. Sorry, it's 0. Here.
I just want to make sure I understand. So the C, the on the left side, C, MTMF, that's the cochains that compute the X groups in mixed-state motives.
I guess so.
No, C is the Lico algebra.
Sorry?
C is the Lico algebra.
Well, okay, there's a kind of difference of notation. So for me, L dot is a Lico algebra, and for Clement it was C for coalgebra. Yes. So it's the same kind of object, suppose. It's just that the letter is different. So no, this is not the chain complex. Well.
The L dot computes the X groups in mixed-state.
Well, if you take the Allenberg complex. Okay, so basically what I wanted to say is, so there is some kind of definition which avoids all of the conditional parts of the theory, and then you can just work with that definition and prove results about it. And the event, I mean, it has a map into, whenever there is a well-defined category of mixed-state motives, there is a map from here to here. So it's like kind of some kind of free version of this construction which doesn't rely on any conjectural parts. Okay, and so that's about as much as I want to talk about the motivic side. So, and now I want to recall what was the connection to the Steinberg module, and that was kind of the more interesting part. So there was a construction which started, so I won't kind of give the motivation, so it will come a little bit later, but you start with a d-dimensional algebraic torus, and I will construct certain elements in this, well, now in this combinatorial Hopf algebra. to do Hn of some field, and this field will be, so there's a lot of freedom in choosing what this field is, because the set of elements I'll pick will be very small. So, but just everything will be contained in all possible algebraic functions on vectors. And I guess it could be much smaller, but I only need kind of to take nth root things. And so, so there was a function which I defined. So Li n A. So it has two sets of indices. Maybe I put semicolon here. So the indices the same way as in the multiple polylogarithms. So there's a set of integers length k, and the matrix with non-zero determinant. So an integer matrix is non-zero determinant. Determinant A. So absolute value will denote by n. And n was the list of indices. All of them are positive. And I guess I had some notation, vector valued notation, but hopefully it will be clear. So I want to define it as a function on the torus or as an element in that space. And it's given by so it's, it would be very nice if the matrix were in GLNC, but otherwise it's a little bit more involved. Y to the power n6. And so what's kind of going on, so some kind of push forward of the function Li n of x. And here, okay, so there's maybe a little bit more of a confusion. So D is any, well, I mean, there's D and there's K, and they're not necessarily the same. So I only want K to be less than or equal to D. And if I have a function of K variables, I think of it as a function of D variables, which doesn't depend on the last K minus D variable. Okay, so it's push forward of a function on the, I mean, on a smaller field, so it's the nx along a surjective map between torus and itself, and it's given by, I mean, I'll just write A, but you should think of it written multiplicative. Okay. And so that was the definition. And so what was nice about it was there is a distribution relation for multiple polylogarism, which, okay, so the first nice property is actually this is a group action. So if I say U and A, okay, it's a monoid action. So if I apply another integer matrix G to this element, and I just define it as GA, this is well-defined action. And actually, scalar matrices just act by as multiplication by powers of scalars. It's going to be scalar to the power n minus d times d n. And so in particular, this group action actually extends to GL dq.
Danilo, yes. Is this the distribution relation what you just wrote down?
This is basically equivalent to distribution. Distribution relation, which I mentioned yesterday. For multiple polylogarithms. So this kind of is a very important part of the story, but
Sorry, I'm a bit confused about your comment about the push forward. If I look at the formula, this looks more like a push forward of the function Li n of x to the a over just the n-fold covering it.
So the formula inside it, there's another application of distribution relation hidden. I mean, it should be the same.
Okay.
Oh, sorry, no, maybe not a, maybe that's what you mean. So it's basically formally what you would do Yeah, so it's with respect to A inverse. It doesn't look like it, but it's that's what it does.
You mean by A, you mean the map x goes to x to the A.
So this is like written multiplicatively. Yeah, x going to x to the A. Yes, except you have to take an inverse, and so this formula is fine. I just wanted to give some motivation. Okay, and then so we had a module which I said LNTD, which was the Q-span of all of these functions. A as A goes over non-zero determinant matrices, the same way as before. And as any sequence of numbers of length less than or equal to d, and weight the sum of n is n. And they quotiented out by everything of the same type which has strictly smaller depths. So I'll just write it. Smaller depths, but not by arbitrary polylogarithms of smaller depths, because that would actually kill the whole module. And by products of a certain type, times Lille and B. It's the Q-span of these. And then the weight would be 1 less. Okay. So it might not look like a good definition, but you can basically ignore what's on the bottom, what you quotient by. So roughly, it is this module, but we want to ignore, I mean, we want to have more functional more kind of identities in certain elements, and we don't really care. There's some kind of great depth filtration, and we want to understand it depth by depth. And so this would be the interesting part. And this is kind of more subtle, so I'll have some comments about it maybe later, so why you have to do this. So this basically makes the coproduct on this space of polylogarithm a filtered coproduct.
So just to make sure I understand, this Q-span and this quotient happens in this combinatorially defined half algebra.
Yes, yes. So everything kind of lives in this space. So it's a huge, huge Q vector space. But we found some, and kind of by the comment before, so this is a GL Q submodule. Well, I mean, there's no action like in general, but it's a module in this space. Inside H and F. And so the main result that I ended the previous talk with was that this GLDQ module is actually, it's not quite a Steinberg module, it's the causal dual Steinberg module. So this is what Jeremy mentioned, I guess. So this is the main result, I guess, and then there's a lot of kind of branches out of it that lead in different directions, so we'll talk about some of them. So the main result is this module ln of TD is isomorphic to, so I'll introduce some notation over here, and I'll explain it in a second. The map is, I have to just do it for generators with respect to the GL action, so I do it.
Did you mean to have two Steinberg factors?
Sorry?
Did you mean to have two Steinberg factors?
Yeah, this is just Steinberg tensor Steinberg over Q, but yeah, so maybe let me do it here. It's not a VB tensor product, it's just a regular. Okay, and so so the map goes well, to an element which I will, L E1 ED. Then there is a certain polynomial, and V is Q to the V. So more canonically, V should be the rationalized character lattice of the torus. But if you just do it like I do, just Q to the power D, and so you have the product here, just product of the vectors. Well, I mean, this is divided power algebra, but this is somehow not the point. Okay, so yeah, so now basically the rest of this talk and the next talk will be maybe not so much proving this result, but exploring what it says on both sides. Actually, so on the polylogarithm side, we care more about the injectivity of this map. And on the Steinberg side, somehow it's interesting that it's surjective. And you can use it to prove, well, I mean, at least to a lot of kind of strange and interesting things.
Then can you say again what L is?
Yeah, I haven't defined it yet. So what L is, so I defined it yesterday, I didn't do it yet. So it's a particular choice of two apartment classes in the Steinberg. So everything that I will do will be given by explicit formulas, which is maybe not what everyone cares about, but in this story, most of the explicit formulas are particularly nice. Okay, so there's that. And now I want to say a few things. Maybe I want to give an example. So here's an example of what this theorem implies. This is for the polylogarithm side. So you can use this to produce functional equations for multiple polylogarithms, which are actually quite non-trivial if you try to do it directly. So, and this is an example I'll come back to at the very end of the next talk. So I picked two integers, alpha and beta, positive integers, and I picked variables x and y, and I'll just denote z to be their product. And so, okay, so claim is, I'll just write an identity for polylogarithms, and then I'll say that it follows from this theorem. So this is an actual identity between analytic functions, so it's not in any motivic or discriminatorial setting, but it of course holds also in those. And okay, so the formula will be maybe a little bit wrong. So I don't know, my handwriting is not very good, but there will be some logic to this formula, so in principle it should be reconstructible. Minus the sum of x, y, and plus, so there's three sums, I'm almost done. X to the I face x and z minus z. And so here there's some kind of summations over capitalized letters, which are given by all possible certain integer power roots of the small lowercase letters. And I mean, it looks kind of terrible, but this is actually just one Lie 1-1-A term in the notation that I defined. So here the matrix you take is this one. So here you take 1, 1, along the data. And here, okay. And this is, again, of the same type, but here the matrix is just 0, 1, 1, 0. And so it's an exercise to just take the claim that I'm making here, take this identity and replace each of these terms by the actual element in the Steinberg H. And you can check that this is an identity in the Steinberg module, except this term goes to 0 in the Steinberg module because it's lower depths. So, yeah. So I just wanted to make like at least one example completely explicit to give you an idea of how it looks. And this is a non-trivial identity, so it means that, well, whatever this map does, actually, some of the things here map to 0. So it's...
So you're saying that to prove this, I basically map everything to the Steinberg module and check it's true there.
Yes, yes. So here, if you know the injectivity of this map, you just check it in the Steinberg module, which is, so for us, that was actually the motivation. Well, not quite that fact, but again, we discovered this isomorphism almost by accident. So what we were after was the result in the polylogarithm mode that I'll state, but will not prove.
Sorry, is there a reason you're like swapping like P1 to P1?
You mean here?
No, on the very top.
Oh, on the very top, yeah. So the problem is, okay, so it kind of it's depending on the convention that you do for the polylogarithms, which way you write this iterated sum.
Oh.
So if we had, and so there is a natural way to see actually why this should be the map, and in fact, so I won't talk about injectivity much, but there's almost a proof of injectivity which just constructs the inverse map, and in that inverse map it kind of has to be like this.
Okay.
And it would be the normal order if we had the opposite convention for polylogarithms, but kind of it's I mean, you don't want to change too many conventions all the time. So once I have this definition, I mean, I don't have to think about this particular case too much. And there's a kind of a lot of nice combinatorial geometry hidden here. So, okay.
Could I ask, in the last equation, what are these matrices you've written underneath?
So this is, okay, so this is, let me call this A1, A2, A3, and then I'm claiming that this is what I call Lille 1, 1, A1 of X, Y.
Aren't they not integer matrices?
No. I mean, these are fractions, right?
Yes. Didn't you say that A was meant to be integer?
Ah, okay, yes, so indeed, but then I said that there is, the group action extends to GLDQ, so I can also do it for, I mean, you can just think of this, yeah, so it's the matrix acting on the pool.
So just dilate until they're integer matrices.
Yeah, I could kind of lift it up, but
I see.
it's a little bit confusing the first time you see. So there is some kind of special property of these three matrices, which is not very visible. I mean, maybe I can state it and then you can check that it's indeed true. So if you look at the first columns of these three matrices, under this condition, they're actually, I mean, they define the same line in Q2. And that's somehow, that's an important point, which kind of, all of these identities will have, but it will be not very clear.
Excuse me.
Yes?
Or will you say something more about this L at the top of the, where that comes from at some point?
This, where this comes from? Well, I mean, at the moment, it's just from the statement of this theorem. So I'm saying this is the map, and the L is just by definition this. So I'm just saying this is a definition of what L is. If you want a more kind of conceptual explanation, I don't know. I mean, it kind of comes out from this trying to understand basically this module, and you after. There's some way to see basically that it should correspond to something in Steinberg tensor Steinberg, and this something should be of this type. So it's just a calculation, but I'll talk a lot about these objects in a bit. So, okay, so theorem, which is the same from the same paper, which is what we actually heard about on the polylogarithm side. So you can use this isomorphism to show identities for multiple polylogarithms. And so the theorem, I'll say it in kind of vague terms, but I'll explain what it means. So in weight n, depth d, all polylogarithms, all multiple polylogarithms can be expressed. And when I say expressed, it's written as a linear combination with some elements in terms of just one function. So the function is Li1, 1 dot 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 n minus d plus 1. So basically, this was kind of what we were after. So we had some kind of conditional proof, assuming Goncharov conjectures that this is the statement is true. And so this isomorphism, actually, you can use it to prove.
So is it all ones?
So it's, everything is 1 until the last one. So basically in depth, so it's a special case, so if you take depth 3, weight 6, there is a formula for Li 2, 2, 2, sum of Li 1, 1, 4, of some, well, I mean, x, y, z, and there is some rational functions of x, y, z. Maybe some coefficients. Okay, so these are the rational functions, but they will be basically the same type of functions that appear in the story, so groups of monomials and exponents. And this is certainly new, so this was not known before. And what's a little bit surprising is that you can find such an identity with such a limited set of arguments here. So it's very simple structure.
Yeah, I mean, I'm sort of wondering what the depth of the right-hand side is.
Here, yes, it's like depth d, and there's 1 plus 1 plus d minus 1 once, and n minus d plus 1, so the weight is n.
But in that one, it's got depth 4 on the right-hand side and depth 3 on the left-hand side.
Sorry, this might, okay, yeah. I mean, I should come up with a different way to write Li. This is EI, and this is 1, 1.
So there's no depth reduction here.
It's not about depth reduction, but this applies in all weights. So in principle, after you go to high enough weights, everything is maximal depth, and then we're saying that among these functions, we actually can figure out just one which spans everything else. Okay, so this may not be more, I mean, this is kind of something more on the polylogarithm side, which doesn't really have any implications on the Steinberg side. So there, I mean, this theorem has a very short proof once you know that, but I'm missing all that time. So what I want to do now, and for the rest of the first and second and third talks, is talk about what this implies on the Steinberg side, which is also not trivial. So, okay, so maybe the second point would be, so I want to say a little bit about what it means in terms of the Kosul duality, but I don't want to spend too much on it. So, so we know that there is a product on multiple polylogarithms. So there is an additional structure here somehow, and so if you don't know anything about Kosul duality of the Steinberg module, it might look a little bit strange because it tells you that there should be some kind of coproduct structure on the Steinberg tensor Steinberg, and indeed it exists. So,
Daniel, can I ask one stupid question? Maybe I didn't listen carefully enough, but did you say where the L lives? Does it live in Steinberg tensor Steinberg?
Yeah. This is in Steinberg H. Yeah, so Steinberg H for me is going to be Steinberg tensor Steinberg.
So do you understand it now inside of Ln as well because of the isomorphism using like, no, I don't know what element in sim.
Well, I mean, on the Ln side, it's just one of the generators. So So it's the standard one. So just
Oh, I see. You wrote it there. Yeah, I see it there. Thank you.
And we send it to this element. And basically, so this is, I mean, this is not just, it's an isomorphism of GLQ modules. So basically, once you act here, you just act on this element in the Steinberg module.
So on the left-hand side, those are generators, and so you know on the right-hand side, those are generators too. And so
not yet. We don't know this. I mean, it is implied by the theorem, but we don't know this yet because these are somehow very special pairs of important classes.
So you want to show that on the right-hand side they're generators, and then imply that the theorem that you wrote there up there that on the left-hand side they're also generators. Is that what
yeah, I guess in a sense. So here, most of the game is actually not about the Steinberg power, but about the symmetric power part. But yeah, so there is a statement about Steinberg module which we use, which you haven't said yet. So you need an additional ingredient here. And that statement actually will be also interesting for just, if you forget about this side completely, in fact, after a certain point in my talk you can do that, so I'm not going to talk about this side that much, but on this side there's a lot of structure you can kind of pull over from the polylogarithm side and prove some results. Well, I don't know. I mean, I'll leave it, but it's not. So this was basically our motivation. So I want to say just a little bit about so-called structure. So yeah, so Steinberg H is a VB Hopf algebra, and so the fact that it's a VB Hopf algebra follows from the Kossel duality that Jeremy mentioned. And so in particular, well, there's kind of some coproduct. There's multiplication, which is not so exciting because it's just given by coordinate-wise multiplication on Steinberg. So it's just, first Steinberg in the first apartment, then the first Steinberg in the second, and the same thing for the other one. The coproduct, so if you know that it's cosumulative, you know there is some kind of coproduct, but actually you don't get any formulas. And the nice thing is from just looking at this a little bit, you can guess the coproduct formula from somewhere in the polylogarithm world. And okay, but so you get explicit formula, which I won't write down because I don't have time. Formula for coproduct. And you also get an explicit formula for how this Steinberg H embeds in the bar complex. So Steinberg H V, so it's isomorphic to the kernel of B, D, Steinberg V, to B, minus 1, where BM, so maybe I give a definition, so BM is a bar construction that is used to compute Tor. And in this particular case, it's kind of an explicit thing. So you take the sum of all the decompositions. I think Jeremy might go this one, but yes, and the fact that this is the kernel actually agrees with the, like, I did a calculation in the first lecture where I showed the coproduct of Li11, and I said it gives you an element in the, it gives you a relation in Steinberg module, and this is kind of the, what's behind it. Okay. I don't think I have that much time to do. So there is a nice formula for the coproduct that you also get, but if it tells you anything, it's very similar to the coproduct of all monopolylogarithms.
And you, I'm a little bit confused about the statement, but not because the statement is unclear, just because. But you proved somehow that there is the compatibility between these two products.
Yes, yes, yes. So, yeah, so there is a stronger version of this result where you put some additional structure. I mean, you have to say exactly what you mean by this coproduct. So this is not a Hopf algebra, but it's also a Hopf algebra in somehow in the VB sense, where instead of vector spaces, you look at the tori and some quotients. And here you have this VB Hopf algebra structure. In fact, it's an isomorphism of VB Hopf algebras. Here it's not, it's like a dual VB. Okay, so, but maybe, so one comment which maybe is more of interest to topologists. So, if you look at this story, I mean, there's a story over Z where we don't know Kusur duality yet, I guess. But we can kind of write what should be the homology if everything works well. So you can define so if you do the BDZ bar construction, where you only allow compositions which respect the lattice. So you only allow the compositions of the actual integer lattice here. So this kernel, well, we conjecture that it should be that it should be the GLD, the submodule times L of E1 ED. And this is kind of the part of the story which is not so clear. So these elements L of E1 ED correspond to polylogarithms at monomials. But for most, so if you just choose arbitrary, well, EIs are columns of some metrics. If you choose arbitrary metrics, it will not be just polylographs of monomials. It will be a huge sum of some radicals of monomials, and so kind of like in the example I have here. So these are some generic matrices with big determinants, and you get a huge sum. And so, but this is somehow, there's a nice subset of all of these, which is just given by polylogarithms of monomials, which are multiplicatively span the character, which spans the character lattice. And it seems like a nice enough object that, I mean, if you kind of believe in analogy, there should be Kusur duality, and this would be the Kusur dual.
Do you have an analogous guess for or generators, or like a description? Well, I guess these would give you generators with Steinberg-Lee. Yeah. But like, do you have an analogous guess for like a basis, or maybe it's not a basis?
The problem is, actually, in this story, the way we understand relations here actually is going through this site. So we can study, I mean, we can define this module. It's fine. It lives in polylogarithms. We don't actually know how to describe all the relations here. So even though we know what are relations in much bigger space, this is a little bit.
Do you also know that's like Steinberg, whatever, is Kazul for Z through like n equals 4 or something? Do you know that?
Oh, you mean how? Yeah, I mean.
Is your conjecture right for small n?
Yeah, for small n it is true. I mean, maybe up to 3 or maybe 4. In fact, there's some version of this which is actually written up in Mono-Goncharov's paper, which is true certainly up to the d equals 3. I'm not sure about d equals 4. So. But I mean, there's some evidence that this is true. So it's not just completely wishful thinking. Okay, and then I don't have that much time. I want to talk about special pairs. So there's more that could be said on the logical side. I just want to do more. I want to do more actual computations in the Steinberg module because it's quite fun, simple combinatorial geometry. And maybe I'll have some comments about how, in general, we do calculations, how to see relations in Steinberg, because I think I've seen Bykowski relation, but there was no, I mean, this geometric interpretation of relations in Steinberg module was not mentioned. Okay, so what are, so I guess it's 3. I want to talk about what we call special pairs, and I think actually in the paper they might be called other pairs. So what I want to do is I want to kind of replace this kind of synthetic formula by something that you can visualize. And so I want to start with recalling what a projective simplex is, and it's just a collection of d points in the d-1 dimensional projective space. Actually, so far the isomorphism in the theorem was only for the field Q. So it was the Steinberg for rationals, and on the polylogarithm side there was now kind of obvious analog what you would do if you replaced rationals by any other field. And this is kind of annoying, but we don't have any replacement for other fields of what there is. But the kind of the combinatorial structure this isomorphism suggests, it holds for all fields. So you can just do combinatories. So P is a simplex. And PQ, so if you have a pair of simplices, with a special pair, well, by definition, P1 should be equal to Q1, and QI should lie in the line between Pi minus 1 Pi, so I and 2 Pt. So what is this weird definition? And now I want to draw some pictures. So I'll do it for d equals 3. So this is simply this P of, well, R3 or Q3. And we have some points, so I think the blue should be Q's, and the yellow should be P's. Okay, so basically I'm talking about this. So you have two simplices, and one of them is kind of inscribed in the second simplex is inscribed in the first one in a certain particular way. So they have one common vertex, and then afterwards, all the vertices of the second simplex lie on successive edges of the first. Okay, so at this point, maybe you'll ask, why am I looking at this? So we have the formula here for the L element. So if I replace some of these labels, you will see that these special pairs are exactly the same as above. So you have I guess you have V3 plus V2, V3 plus V2 plus V1. So I'm going to write it like this, and so the blue ones, one of them is the same, and then you have the rest like this. So basically I'm taking these two tuples of vectors and I'm drawing a projective picture. And so what's nice about this projective picture is actually it keeps all of the information about the element L. So, so this a priori, if you cannot kind of rescale the vectors VI individually, so there is no. So L is not something defined on a collection of projective lines. So it actually depends on the scaling of the vectors you choose. Because there are some kind of additions inside that. But if you kind of take both sets of points and put them together, so this projective picture actually remembers the whole collection of vectors up to scale, which is kind of a nice simple exercise. So what this means for us is that we can, so the other comment is that what are the relations in Steinberg? So this is not quite the same picture as we had before when we visualized Steinberg elements, I think. So that was more like abstract simplicial complex, and here I'm actually looking at the actual projective space, and I'm drawing an actual simplex. And so if you think about these terms, if I think about V1, V2, V3, so this is in Steinberg, V, and I kind of associated to it a projective picture like this. So I associated to it kind of a simplex in P. Then what are the relations that you have in the Steinberg module? Well, you have the obvious ones, which are, you can rescale anything, and it only depends on actual, not on vectors, but the lines that they generate, which you already have it here because it's projective. And the other thing that you have is you can permute the vertices, and then you acquire a sign. So you basically think of this simplex as something with orientation. And the non-trivial relation comes from the decomposition of this thing. So you basically, you're turning it into a number of simplices and writing it down. So what I mean by this, if I have another point V4, then so V1, V2, V3 is going to be, I mean, if I do everything correctly, which I probably will not. V4, V3, V1, V4, V2, V3, maybe. So this is one of the generators for all relations in the Steinberg, and this just corresponds to the fact that you take this triangle and you cut it into sum of three triangles. Okay. And this will allow me to prove statements about Steinberg module by just drawing pictures. Well, at least in the case d equals 3, which is nice. And I think, am I already out of time, or? Time is up. Okay, then let's continue after the coffee break.